Right now, as you're watching this video, somewhere out there an automated scanner is probing a freshly deployed Linux server. It doesn't care who owns it. It doesn't care what it's for. It just found an open port, noted the default configuration, and added that server to a list. That server might be yours. And the scariest part? This probably happened within the first 10 minutes of deployment, before you even finished reading the setup documentation. I've spent years working with Linux servers, and the one thing that keeps me up at night isn't sophisticated zero-day exploits or nation-state attackers. It's something far more embarrassing. It's the defaults. The boring, invisible, factory-setting defaults that every Linux distribution ships with. Because those defaults weren't designed to protect your server from the hostile, scanner-filled internet. They were designed to make installation smooth. And that decision, made by someone you've never met in a context that has nothing to do with your infrastructure, is silently undermining every server you've ever deployed. Today, I'm going to walk you through exactly what those dangerous defaults are, show you real exploitation scenarios, and give you the precise commands to fix all of them. By the end of this video, you'll have a hardened server. Not someday, tonight. Let's start by understanding why this problem exists in the first place. Because it's not incompetence. It's a genuine trade-off that distribution maintainers have to make. When you're building a Linux distribution, you're serving two very different audiences simultaneously. On one side, you have beginners who need a smooth installation experience, something that just works out of the box. On the other side, you have production administrators who need a locked-down, hardened system. If you ship defaults that are too restrictive, beginners get frustrated, adoption drops, and the distribution loses the community support it needs to survive. So maintainers choose accessibility, they make the install friendly, and they assume that administrators, people like you and me, will handle the security hardening afterward. The problem is that afterward is a dangerous word when automated scanners are measuring discovery time in minutes. Shodan, the search engine for internet-connected devices, has documented this in painful detail. Their data shows that a newly provisioned server with a public IP address gets its first automated probe within minutes. Not hours, not days, minutes. By the time you've finished deploying your application and told yourself, I'll harden it tomorrow, your server has already been discovered, fingerprinted, and cataloged by dozens of automated scanning systems. They're not attacking yet. They're just waiting. Waiting for the credential that brute force eventually cracks, waiting for the service vulnerability that the next disclosure makes exploitable, patient, automated, relentless. The Verizon Data Breach Investigations Report, one of the most comprehensive annual studies of real-world cyber attacks, consistently places default credentials, default-enabled services, and misconfigured systems at the top of the list of attack vectors responsible for server compromises. These aren't theoretical vulnerabilities being discussed in academic papers. These are the actual techniques that are filling actual incident response reports at actual companies. And the common thread across all of them is the dangerous default configuration that nobody got around to fixing. So let's talk about what those dangerous defaults actually are. Starting with the one that gets more servers compromised than almost anything else. SSH, Secure Shell. The protocol you use every single day to manage your servers. In its default configuration, SSH is about as secure as a screen door. And I mean that literally. Here's what the default SSH configuration on most Linux distributions looks like the moment you provision a server. Password authentication is enabled, root login is permitted, the service is running on port 22, and connections are accepted from any IP address in the entire world. Let's break down why each of those things is catastrophic. Password authentication means that anyone can attempt to log in by guessing passwords, and they don't have to guess manually. There are automated tools that hammer SSH servers with millions of username and password combinations per hour, pulling from databases of billions of credentials leaked in past data breaches. If you've reused a password, or if your password is anything less than truly random, these tools will eventually find it. There's no lockout by default, no consequence for trying a million times. It's like having a combination lock on your front door, but allowing unlimited guesses. Permitting root login is even worse. When an attacker authenticates directly as root over SSH, they get complete system access in a single step. No privilege escalation required, no audit trail of how they got there, no intermediate account that might trigger an alert. They're in, and they're in as the most powerful user on the system. Running SSH on port 22 is essentially announcing your presence to every automated scanner on the internet. Port 22 is the first port these tools check specifically, because SSH is there by default on every Linux server ever deployed. Moving to a non-standard port won't stop a determined attacker, but it will dramatically reduce the noise, the constant background hum of automated brute force attempts that your logs fill up with every single day. And accepting connections from any IP address in the world when you know perfectly well that your legitimate administrative Connections come from a handful of specific addresses. That's just leaving the door open when you know exactly who's supposed to walk through it. Here's how you fix all of it. Open your SSH daemon configuration file with sudo nano etstar ssd config. Find the line that says password authentication and change it to no. Before you do this, and I cannot stress this enough, make absolutely sure your public SSH key is already in the important SSH authorized keys file for your user account. If you disable password authentication without setting up key-based auth first, you will lock yourself out of your own server. I've seen it happen. It's not fun. Next, find permit root login and set it to no. From now on, attackers would need to compromise a regular user account and then escalate privileges. And that escalation creates the audit trail you need for detection. Find the port directive and change it from 22 to something above 1024. Well, pick a number that's memorable to you, but not an obvious alternative like 2222. Add an allow users directive followed by only the specific usernames that actually need SSH access, and add max auth tries 3 to limit how many password guesses can happen per connection before the session is terminated. Save the file, restart SSH with sudo systemctl restart SSD, and verify it's running before you close your current session. Now for the second dangerous default, and this one genuinely shocks people when they realize what it means. On most Linux distributions, at the moment of deployment, there is no firewall at all. Zero. Every port that any service is listening on is fully accessible from the entire internet. Think about what that means in practice. You install a database to support your application, MySQL, PostgreSQL, MongoDB, doesn't matter which. The installation process, by default, often binds that database to all network interfaces. You meant to configure it to only listen on localhost. You were going to do that right after you finished getting the application up and running. But the application took longer than expected, and now your database port is sitting wide open on the public internet with no firewall blocking access to it, possibly with default or no credentials. The scanners know this. They probe for open database ports across the entire IPv4 address space continuously. When they find one, they don't need to compromise your application layer or crack your SSH credentials. They just connect directly to the database and read everything. Your user table, your credentials, your customer data, your entire business, accessible because there was no firewall, because the default configuration assumed you were operating in a trusted internal environment. Fixing this is straightforward, but requires deliberate thought about what your server actually needs to be accessible from the outside. Start by installing UFW, the uncomplicated firewall, with sudo apt install UFW on Debian-based systems, or configure firewalled on Red Hat-based systems. Set the default policy with sudo UFW default deny incoming and sudo UFW default allow outgoing. This means nothing gets in unless you explicitly allow it. Then add only the rules you actually need. If your server runs a web application, allow ports 80 and 443. Allow your custom SSH port. If you have other services that legitimately need external access, allow only those specific ports. Enable the firewall with sudo UFW enable, and verify your rules with sudo UFW status verbose. Read through that output carefully. Every open port is an attack surface. Make sure every open port is one you consciously chose. The third dangerous default is what I call the bloat attack surface. All the services that Linux distributions install and enable by default, because they might be useful for some use case, running silently in the background of your server, consuming resources, exposing attack surfaces, and serving absolutely no purpose on your specific server. The one that got the most attention recently is CUPS, the Common Unix Printing System. In 2024, a critical remote code execution vulnerability chain in CUPS was disclosed that sent the security community into a frenzy. Servers running the CUPS service were vulnerable to complete remote compromise. Know who had CUPS running? Every server where nobody had thought to check whether a print spooler was necessary on a machine that would never in its entire operational life be asked to print a single document. Beyond CUPS, default installations often include mail transfer agents like Postfix or SendMail exposing SMTP to the internet, RPC services creating port mapper exposure, and Avahi daemons running MDNS service discovery on systems that have no use for local network discovery whatsoever. Each of these services is an attack surface. Each one has a vulnerability history, and each one is running on your server not because you need it, but because the distribution installed it by default. The fix is a systematic audit. Run sudo systemctl list units, type our service, state are running to see every active service, and sudo ss tlnp to see every listening network socket and which process owns it. Go through that list and ask yourself, for each service, does my server's actual function require this? If the answer is no, stop it and disable it. Sudo system stop service name, followed by sudo system disable service name. Do this for every service that doesn't have a clear reason to exist on your server. Less attack surface is always better. The fourth dangerous default lies deeper in the system, in the kernel itself. The sysctl parameters that govern how the Linux kernel handles networking, memory, and security behaviors ship with defaults optimized for broad compatibility, not for resistance to attack. And several of these defaults create significant vulnerabilities. IP forwarding is enabled by default in some configurations. Unless your server is functioning as a router, deliberately forwarding traffic between network segments, this capability should be off. A compromised server with IP forwarding enabled can become a relay for attacks on other parts of your network. ICMP redirect acceptance is enabled by default, which means an attacker with network access can potentially manipulate your server's routing decisions. CWIN cookie protection, which defends against CWIN flood denial of service attacks, is often not enabled by default. Kernel pointer exposure through the proc file system, which gives attackers the address space layout information they need to defeat ASLR, is permitted for unprivileged users by default. Open.job, etc. says ktl.don89security.conf with pseudonano and add these parameters. Set net.ipv4.ipforward 0 to disable IP forwarding. Set net.pv4.conf.all.send redirects from 0 and net.ipv4.conf.default.send redirects from 0 to disable ICMP redirect sending. Set net.ipv4.conf.all.accept redirects from 0 and net.ipv6.conf.all.accept redirects from 0 to disable redirect acceptance. Set net.ipv4.dip.syn cookies or kernel.1 to enable syn flood protection. Set kernel.randomize or space from word 2 for full address space layout randomization. Set kernel.kptr restrict word 2 to restrict kernel. Pointer exposure to privileged users only. Set net.ipv4.conf.all.rp filter -1 to enable reverse path filtering against IP spoofing. Save the file and apply everything immediately with sudo sysctl p etc sysctl.d99security.conf. The fifth dangerous default is in your user and privilege configuration. And this is where initial access gets converted into full system compromise. An attacker who has gained any foothold on your system through any means will immediately look for privilege escalation pathways. And the default Linux configuration provides several. Default installations often include user accounts created during setup, whose necessity for your specific server's function has never been evaluated. Some deployment tools and cloud providers create an initial admin user with essentially unrestricted sudo access, meaning that compromising that one account gives an attacker root-level control over everything. CUID binaries with programs that run with elevated privileges regardless of who executes them accumulate on systems over time, and each one represents a potential privilege escalation vector. Start your audit by reviewing stash etc. password to identify all user accounts and lock any that your server's administration doesn't require, using sudo usermod s.sbin knowledge username. Review your sudo configuration with sudo vsudo. Look for all as all grants, and replace them with specific command lists that cover only what each user actually needs to do administratively. Or audit your SUID and SGID binaries with find, perm, 4000, operm, 2000, 2, devnull, and remove elevated permissions from any binary that doesn't require them with sudo chmod US binary path. The sixth and final dangerous default is the one that makes everything else worse. Insufficient audit logging. When an attacker compromises a system, they typically take time to explore, harvest credentials, install persistence mechanisms, and move laterally to other systems. If your logging configuration isn't capturing the right events, all of that activity happens without leaving a trace. When you eventually discover the breach, and discovery often comes weeks or months after the initial compromise, you have no forensic evidence to understand what happened, what was accessed, or how far the attacker spread. The default logging configuration on most Linux systems captures a subset of system events. It misses authentication failure patterns that would identify brute force attempts. It misses privilege escalation events, the sudo and su executions that show how an attacker moved from user to root. It misses file access events on sensitive files like etc. past and etc. shadow. It misses the Network connections that reveal command and control communication and lateral movement. Install and configure the audit daemon. Sudo apt install auditd on Debian-based systems, then enable and start it. Configure audit rules with sudo auditctl to capture authentication events by watching jjardvar log.auth.log, privilege escalation with wsu usr bin sudo pxk, privilege escalation, credential file access with a wu etc password p by the way k identity and w etc shadow p way k identity, and SSH configuration changes with w etc hgshtr config p the way k ssh config. Make these rules persistent by adding them to etc audit rules.d-audit.rules. Configure log rotation to retain audit logs for long enough to support incident investigation, at minimum 90 days, longer if your compliance requirements demand it. Now, I want to be honest with you about what this hardening does and doesn't protect you from, because false confidence is its own security risk. Everything we've covered tonight addresses the default configuration exploitation that fills the vast majority of incident response reports. It dramatically raises the bar for an attacker trying to compromise your server through automated tools and common attack techniques. What it doesn't protect you from is a zero-day vulnerability in your kernel or system software, a flaw that patches don't exist for yet. It doesn't protect you from supply chain compromise, where malicious code is inserted into trusted packages. It doesn't protect you from sophisticated social engineering that obtains your legitimate credentials. These attack categories require different mitigations: regular patching, package signature verification, multi-factor authentication, and security monitoring that goes beyond what we've covered here. But here's the reality. The vast majority of Linux server compromises don't involve any of those sophisticated techniques. They involve automated tools, finding default SSH, configurations, default configured databases exposed to the internet, unnecessary services with known vulnerabilities, and broad pseudo grants that convert initial access into root access. Fix the defaults, and you've eliminated the attack vectors responsible for most of the breaches in the incident response literature. The distribution maintainers who shipped these defaults weren't malicious. They were making a genuine trade-off between accessibility and security, assuming that administrators would handle hardening before internet exposure. That assumption, reasonable in an era of slower scanning and less automation, has been rendered dangerously outdated by the current reality of continuous, automated, comprehensive internet scanning that finds and catalogs your server within minutes of its first network response. Every server you've ever deployed started its life exposed. Every one. The server running your application, the one hosting your database, the one serving your customers, the one storing the credentials that connect your entire infrastructure. Each one launched into a hostile network with password authentication enabled, no firewall, unnecessary services running, permissive kernel parameters, broad privilege grants, and insufficient logging. The scanners found them the day they were provisioned. They've been probing the defaults ever since. The remediation exists. Every command in this video is something you can run tonight. SSH hardening takes 10 minutes. Firewall configuration takes 15. Service audit takes 20. Kernel parameters take 5. Privilege review takes 30. Audit logging takes 20. That's under 2 hours total to transform every server you're responsible for from the default configured attack surface that the distribution installed into a hardened system whose security posture actually reflects the environment it's operating in. Compare that to what a compromise costs: the incident response engagement, the forensic investigation that might take weeks and still not tell you everything the attacker accessed because the logging wasn't there, the customer notification if personal data was involved, the regulatory consequences if compliance requirements apply, the reputation damage that follows a disclosed breach, the rebuild from scratch, because you can never fully trust a compromised system, the months of investigation, remediation, and recovery that a single exploited default configuration makes necessary. The terminal is already open on every server you manage. The commands are in this video. The choice is whether you make tonight the night you fix the defaults, or whether you leave that work for later. The same later that's been accumulating since the day you provisioned those servers. Open the SSH configuration. Disable password authentication. Configure the firewall. Stop the unnecessary services. Apply the kernel security parameters. Audit the user privileges. Enable the audit daemon. Do it in that order on every server you're responsible for, starting tonight. Because the automated scanner that found your server the day you deployed it is still out there. It's still probing. It's still waiting. And the only question left is whether you fix the default before it does what the default makes possible. The terminal is waiting. Start with SSH. Go fix your servers.